humans live very much in the middle of things, and our senses are tuned to perceive things in the middle range. Let's start with size. If you laid human bodies end to end, it would take about 25 billion of them to reach Venus, our nearest neighbouring planet. Going the other way, a similar number of atoms would be needed to match the length of a human body. We are also in the middle when it comes to time. A typical human lifetime lasts about 1 billion seconds, and it would take about 250 million human lifetimes to match the age of the universe. So, just how much of this can our human eyes make out? Well, with the naked eye we can see down to about 1/10 of a millimetre, or 100 micrometres. That's about the thickness of a human head hair. And with a simple magnifying glass we can get down to perhaps 20 micrometres. The very first microscopes consisted of little more than small glass spheres. But with better single lenses, Dutchman Anton van Leeuwenhoek soon revealed many surprises about small things. The images were still rather poor, however. Compound microscopes with more than one lens can do much better, and Robert Hooke famously showed the world sights that had never before been imagined. So let's see what there is in a drop of pond water. The best light microscopes are able to resolve 0.2 micrometres or 200 nanometres. But why no further? Well, it's all to do with the nature of the light that we use to see with. Light is electromagnetic waves. It consists of photons that can be best thought of as small wave packets. Now, imagine trying to form an image with these photons. If they're much smaller than the detail we wish to see, it's easy to make an image. But what if we want to make out finer detail? Not much to see there. We need to use smaller particles, or shorter wavelengths. Back to the electromagnetic spectrum, and we see that in order to have these shorter wavelengths, we would have to use ultraviolet light, or perhaps even X-rays or gamma rays. There's a snag though. We can't make lenses to produce images from these shorter wavelengths. This is where electron microscopes come in. The first electron microscopes worked in a somewhat similar way to light microscopes, but used electrons in place of visible light. These can have much shorter wavelengths, but can't be focused using glass lenses. We have to use magnetic lenses. The beam of electrons passes through an extremely thin slice of specimen, and is then focused onto a fluorescent screen, or photographic film. But what if we don't have a very thin specimen to look at? This is where a different device comes in, the scanning electron microscope. Instead of the electrons going through the specimen, a very fine beam is made to scan across it, in much the same way as a cathode ray tube does in a television set, but only covering a tiny area. The scattered electrons are collected, amplified, and displayed across a large screen to form an image. This allows us to look at solid objects. And there's yet another way of imaging things on the atomic scale. It's the scanning tunneling or atomic force microscope. It works by having an extremely sharp stylus, just one atom wide at its tip, which scans across the surface of the specimen. It's almost, but not quite, touching it. By sensing the forces between the atoms, the stylus feels its way over the specimen, like a hovercraft on rough ground. And these vertical movements are turned into an image. This allows us to see individual molecules in surprising detail. Back to our familiar size, to think about how we can look at really large objects. Not really a problem, of course, in most cases. But when they're huge distances away across the universe, they can begin to look rather small, so we have to use telescopes. With devices such as the Hubble Space Telescope, we can now see the most amazing objects scattered throughout the universe. Just some of the things that we can see using visible light. Now, let's go back to the electromagnetic spectrum and see what uses we can make for other parts of it. But first, a reminder of just what our eyes can see. It's 400 nanometers for blue, up to 700 nanometers for red, right in the middle of the spectrum. As we move to shorter wavelengths, we come to ultraviolet, best known as that part of sunlight that gives us a tan. This is being shot using ultraviolet light, but apart from the fluorescence of my shirt, there's not much that either our eyes or the video camera can see. Although we can't see UV, many insects can, and some flowers have taken advantage of this to guide pollinators towards the nectar and stamens. At wavelengths a bit shorter still, we're into the world of X-rays. Discovered in 1895, they soon found applications imaging broken bones, shown here as the simple shadowgraphs still used in many hospitals. Simple X-rays are not ideal for imaging soft tissue, however, and these single-shot photos can easily miss vital detail. Recently, however, advanced computing has been added to give computer tomography, or CT scans. A thin rotating X-ray beam passes through the body and is collected by an array of detectors. After processing, it gives a detailed image that would have been unthinkable to early radiographers. Briefly into outer space to see what these shorter wavelengths can show us. This is how our Sun looks in ultraviolet and X-ray light. And this shows how different a galaxy can appear when we move from visible light into the ultraviolet region. Now, let's go back through the spectrum, through visible light and on to longer wavelengths. First, we come to infrared radiation, often associated with radiated heat. Just beyond visible red light, in the near-infrared range, the world takes on yet another appearance. Foliage, for instance, reflects infrared very well, so trees look as if they're covered in frost. Near-infrared can also be used to see in the dark, again by using radiation reflected from objects, in much the same way as our everyday vision. Right now, I'm being illuminated with visible light, and now I'm being illuminated with infrared light. But there's yet another way of using infrared to see things. We can use the infrared given off by hot bodies. This is called thermal imaging. The wavelength of the infrared rays depends on the temperature, and by assigning a different colour to each temperature, we can see just how hot each part of the subject is. Thermal imaging can be used for everything from catching escaped criminals to medical examinations or solving industrial problems. Beyond infrared, we come to terahertz or T-waves. These have recently, and rather controversially, been used to image contraband under clothing. It's just that they also show other things, and perhaps rather too well. A bit further along and we come to microwaves. With wavelengths from a few centimetres to several metres, they're suited to imaging larger things and are the basis of radar. With radar, a beam of microwaves is sent out and its reflections are collected and shown on a screen.
Runway 7, hold, correction, runway 12, hold.
Thanks to the radar on all ships, planes and airports, the world is now a much safer place.
Emma, how's it going? X31, ready to check, thanks to 12. Tango 3 left turn again.
Celestial bodies also give off microwaves and can look very different when viewed in this way. One benefit is the ability to see through dust clouds to reveal such things as the very centre of our own galaxy, the Milky Way. Back to Earth, to visible light and more familiar dimensions. This visible light still has a few more things to offer when it comes to making images. Firstly, there's polarized light. The waves of ordinary light vibrate in all directions, but if we pass it through a polarizing filter, we're left with light vibrating in just a single direction. Light from a blue sky is naturally polarized, and we can use a filter to darken it and make clouds stand out. Rays reflected off non-metallic surfaces, such as glass, can also be highly polarized. A filter will help remove these annoying reflections. Send light through one polarizing filter and then through another at right angles, and we can stop all the light from passing. Put certain materials between the filters, they rotate the direction of vibration, letting the light through again. Each colour is rotated differently, however, and a whole new world now appears. For example, we can see the structures within materials and how much stress is present, an invaluable tool. Watching crystals in this way can give some really beautiful images. Another optical technique allows us to see the different densities in gases and liquids. It's called Schlieren photography and can be used for things such as studying the flow of air around a plane's wing. When using apparatus a bit like this, it can produce yet another kind of stunning image. A final trick using visible light is holography. It uses the interaction between two laser beams, and we can see the effect using a ripple tank to make waves on the surface of water. See the pattern where the original waves meet those reflected from an object. The same thing can be done with light, but in 3 dimensions, using a setup rather like this. The light waves coming directly from the laser meet waves reflected from the teapot to give a hologram. When the hologram is viewed in a correct way, we recreate the original scene, but in 3 dimensions. We can now look around objects. So far, most of what we've seen has taken place at speeds that we humans can easily comprehend. We can't perceive motion that takes place in less than about a 25th of a second. It all becomes a blur. Similarly, any movement that takes place over, say, several minutes, think of the hands of a clock, can be equally difficult to appreciate. Our familiar films and videos typically work by taking 25 still pictures or frames every second, and then playing them back at the same speed to give the illusion of motion. This works because our eyes can't perceive motion that takes place any faster than this, and blurs the images into one continuous movement. Let's take a look at the super fast and slow things down a bit. This means taking pictures at a much faster rate than 25 per second and then playing them back at the usual rate. Everything is slowed down and we can see things that would otherwise be lost to us. Now, let's make things appear much faster than in reality. with time-lapse photography. Moving away from the electromagnetic spectrum, what other ways are there of forming images? There are now quite a few that are becoming familiar to us through medical diagnostics. fMRI is rather complicated and involves the subject being placed in a very strong magnetic field and exposed to pulses of radio waves. When looking at, say, a living human brain, the strength of the signal depends on blood flow, which in turn depends on how much activity there is at each point. In this way, we're almost able to actually watch people thinking. PET, or positron emission tomography, can give rather similar results, but works in a completely different way. A tiny amount of short-lived radioactive material is injected into the bloodstream and collects in places where there's the greatest metabolic activity. By analysing the positron radiation given off, it's possible to make an image showing just how a particular organ is functioning. Another imaging technique, now becoming familiar in hospitals, is ultrasound. This uses sound waves of such high frequency or pitch that we can't hear them. Ultrasound waves pass easily through the body, but are reflected by any changes that they encounter in the tissues. The reflected waves are collected and, just as with a radar signal, turned into an image. Nowadays, the first baby photographs are often taken long before the new member of the family is even born. So, back to the middle, but this time the middle of a rather small human body. We now have imaging techniques that seemed far-fetched when we first saw them a few decades ago in Star Trek. Today, they're becoming a commonplace. Who knows what we might be able to see in the next decades?